Hey everyone, welcome back. Hope you're all having a good day. So in this video today, this is going to be a continuation of what we learned in the last video, which was series and parallel circuit. So if you haven't seen that, you can go watch that. But pretty much today we'll be working on some example problems to test out what we learned, except these problems are actually much more difficult than the last video. We'll just be working with series and parallel circuits that will coexist in a single circuit, and our job is to simplify the circuit such that it goes from the complex form it had originally to the point where it has fewer resistors, maybe even one resistor in the end, so that we could use Ohm's law to calculate the current flowing throughout the resistor, and then we could even go as far as to calculate the individual voltage drop of each resistor, but that's not the main focus of this video. We can cover that in a different one. So yeah, if you're excited, let's get started, and feel free to take some notes along with me. Okay, so problem number one here, we have a circuit with a 12-volt battery that is supplying voltage to three different resistors here, as denoted by R1, 2, and 3, and they each have their own individual resistor value. And right off the bat, we can see that R1 and R3 are in parallel with one another, so we can simplify that by using this formula here. So the equivalent resistance between R1 and R3 will be 1 over R1 plus 1 over R2, and then raising all that to the -1 power. So if we plug in our values here, R1 is 10 ohms. I'm just going to leave out the units for simplicity. And R3 is 5 ohms. And once we add that up, we can raise it to the negative first power. That will be 3.3. So now we're not done yet, but we can take the original circuit we had here and redraw it with our new found value. So here's the 12-volt battery here, and then we have two resistors this time since we eliminated one of the resistors from our first attempt. So this is going to be resistor 2, which still remains 20 ohms, and then this is going to be 3.33 ohms, which is the equivalent resistance we found from over here, and that represents R1 and R2. So from here on out, it's very simple. We simply just add these two values together. So that should give us a total resistance of 23.33 ohms repeated. And now that we have that, we can once more redraw our circuit. So it's going to have only one resistor this time. Whoops, I don't know what happened there. And we still have the 12-volt battery here, and then this single resistor is going to encompass all the other resistance values. So it's going to be 23.3 repeating ohms. And let's use Ohm's law to calculate the current. So plugging what we have into the formula, we can do I equals 12 volts divided by 23.33 repeating, and that should give us approximately 0.514 amps. So that's it for this example. 0.514 amps of current is flowing throughout the resistor. So let me write that down right here. So current is going in this direction, and we have 0.514 amps, and it's going to go in this clockwise manner. So that's all for this example. Let's move on to the next one. Okay, so here's another problem that you guys can try out. How would you tackle this, given that we have multiple resistors in both series and parallel? Well, first, it's important to realize that R1 and R2 are in parallel because they are directly across from each other. So let's find the equivalent parallel resistance for these two values. So that's going to be 1 over 12 if we use the inverse formula we had earlier, plus 1 over 4 raised to the -1 power, which will simply give us 3 ohms. And now that we have that, these two resistors come together as one, so they are now in series with the 6 ohm resistor, which is the R3 resistor. So we can add 3 and 6 together to get 9 ohms. So we know that R1 is parallel. I'm going to use this symbol here for parallel, and this entire parentheses represents 3 ohms, and we're going to add that to R3. So that's going to be 3 ohms plus 6 ohms, which is 9 ohms. So now we've solved for these three resistors, but now let's take R4 into account. So to recap, 9 ohm represents the equivalent resistance between R2, R1, and R3, because R1 and R2 are in parallel, therefore they come together as one to form 3 ohms up here, and then once we get 3 ohms, we add 3 to 6 to give us 9. And now that we have all three of these resistors as a single value, you'll notice that 9 ohms and 8 ohms for the R4 resistor are also in parallel. So we can take that entire group and calculate the equivalent resistance for those. So it's going to be 1 over 9 plus 1 over 8, raise that to the minus 1 power, and that's going to give us approximately 4.235 ohms. So that's our total resistance in this parallel and series circuit combination circuit. As you notice that as we added more resistors in parallel, the total resistance actually went down because we actually had some pretty high value resistance like the 12 ohm resistor for R2 and the 8 ohm resistor for R4, but in the end we ended up with a resistance value that is less than any of those individual resistor values. So it's important to remember that in parallel circuits, resistance decreases as you add more resistors in parallel. So hopefully that made sense, and now let's go on to example number 3. Okay, so here's another more slightly difficult example. So we have once more a parallel circuit with 3 resistors in parallel. So let's start by finding the equivalent resistance of all of these 3 resistors. So the formula we're going to use is the resistance equivalence formula. So it's going to be Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and once we get the summation of all that, we're going to raise it to the negative 1 power. So plugging in what we have, it's going to be 1 over 5 plus 1 over 10 plus 1 over 15 raised to the minus 1 power, which is going to be 2.727 ohms. So now that we have this value here, we can substitute that in for all 3 of these resistors by redrawing the entire circuit. So if we scroll down, we're going to have this new circuit with 2 resistors this time. So this is our original 20 ohm resistor, which represented R4, and this is our equivalent resistance. And you'll notice that these resistance are in parallel, or rather they're in series with each other. So all you have to do is add up their values as it is. So we can redraw our circuit again with 1 resistor this time with the value of 22.727 ohms. And we still have 24 volts, so let me label that there. So from here on out, we just have to use Ohm's law. So it's going to be V equals IR, solving for I, that will be voltage over resistance, and plugging in what we have, it'll be 24 volts over 22.727 ohms. Actually, I don't know why I wrote 24. In my notes, it's supposed to be 12. So we have 12 volts to divide by this value here. So that will give us 0.528 amps flowing throughout the circuit. So let's scroll back up and label our findings. We basically have 0.528 amps of current being distributed throughout the circuit. So it's going to go through this branch here, and then make its way back to the battery. And now that brings us to our last example for the video before we wrap up. Okay, so for our last example, I came up with a fairly difficult challenge, but hopefully you guys can figure it out. So if you want to, feel free to pause the video and take a second to solve it. So the first thing we want to look for is to identify any parallel resistors which exist in the circuit, which in this case it does. So we have R1 and R2 right here. Let me circle it for you. So these are in parallel with one another, so we can use the inverse formula again. So it's going to be 1 over R1 plus 1 over R2, and raise all that to the negative 1 power. So it's going to be 1 over 10 plus 1 over 20 raised to the negative 1, which will give us 6.6 ohms repeating. So we can replace all of this with a 6.6 ohm resistor. And now that we have that in mind, we can identify and see that the 6.66 ohm resistor is in series with this R3 resistor right here. So we can add 5 ohms to our resistance right here, which will give us 11.66 ohm. So now let me change this to a different color. So this entire group right here can be represented by this 11.6 ohm resistor, meaning that it is now one resistor. So the 11.66 ohm resistor is also in parallel with R4. So we can take 1 over 11.66 plus 1 over 30, which is the resistance value of R4, and then just raise all that to the negative 1 power, which if you type that into your calculator should give you exactly 8.4 ohms. So once again, let's change this to a different color. So R1 all the way to R4 can be represented by the 8.4 ohm resistor. So we're slowly simplifying the circuit down to fewer resistors. And now that we have the 8.4 ohm encompassing all 4 of these resistors, you'll notice that if we replace all these resistors and put the 8.4 ohm in, then the 8.4 ohm resistor will be in parallel with R5 and R6. So we just simply add these two values to 8.4. So it's going to be 8.4 ohms plus R5 plus R6, which will give us our total resistance, which will be R2 in this case. So if we just plug in what we have, it's going to be 8.4 ohms plus 8 ohms for the R5 resistor, and then 12 ohms for R6, which is simply going to be 28.4 ohms. So we're technically done now. We found the total resistance in the circuit. So let's redraw the original circuit, but only include the 28.4 resistor, which is the equivalent resistance, also the total resistance. So here's our circuit right here, and there's our resistor, and this is going to have the value of 28.4 ohms. This simple resistor right here that you see here technically has the same amount of current flowing through it as this complicated looking circuit we originally had. So that's kind of the beauty of simplifying combination circuits. So I hope I'm able to get that point across to you guys in this video. So once again, we have the 24 volt battery right here, and we're going to have some amount of current flowing throughout the circuit, which we don't know what it is yet, so that's why we're going to solve for it. So going back to Ohm's law, current is simply just the voltage divided by the resistance, or the total resistance if you're dealing with more than one resistors. So the current is going to be 24 volts divided by 28.4 ohms, which will come out to be around 0.845 amps. So that's how much current we have flowing through this resistor. And if you want to, you could also calculate the voltage drop across each of these individual resistors, like R1 all the way to R6, but that would probably take up another 30 to 40 minutes if we did that for all the examples, so that'll be a topic for another video. Anyways, I hope you guys enjoyed this video and learned something new, and I hope you found some value out of it, and I'll see you in the next video. Have a great day.